And we'll pick up from current slide. I think we will. There we go. Now, ooh. There, I think that is where we were beginning this time. All right, any questions from before? Okay. This is example, oh, well, no. We just finished example 3, and we went to the next of our forms. And again, I don't really care for this one. It's fine. It's perfectly fine. It may be standard. But I want you to remind me what I use for the, say, spheres. What was the standard type equation for a sphere? Remember that one? It was a special case of a ellipsoid, where all the axes are equal. Actually, I'm going to back off. I may not have actually said it. Yes, exactly. Okay. X. I didn't. Yeah, right. Okay. Sorry, I realized that. X over r squared plus y over r squared plus z over r squared is equal to 1. Now, that's not how we usually write it. We'd write it as x squared plus y squared plus z squared is equal to r squared. That would be the standard. I mean, that would be the most common way. But getting it into the same form that we're doing the others, that's how I would do it. Now, I realize now I didn't actually do that one before. I think I did it with a circle, but didn't take it onto a sphere. So, ellipsoid would be a more general case of this. What would that be? Yeah, x over a squared plus over b squared plus z over c squared, and that would be equal to 1. Okay? Next sort of general form. That would be a sphere is enclosed, an ellipsoid is enclosed. Now we get the ones that are more open. X over a squared plus y over b squared minus z over c squared is equal to 1. What would that be? Yes, a hyperboloid of 1 sheet. Okay? And then, this is the way the book does, but I like to do it this way. X over a squared minus y over b squared minus z over c squared is equal to 1. That would be the hyperboloid of 2 sheets. Now the book usually writes it, these two with pluses, and then this one minus 1, okay? And that's perfectly fine to write it that way, but it just looks like to me this is more orderly, regular, okay? Now, say that again. Okay, say that one more time. The signs is minus y and minus. Okay. Now, remember, okay, let's back off here. These, everything's legitimate. I mean, equivalent. Doesn't matter where your axis is, it's still over your sphere. This one, the larger one of those numbers is going to be your major axis. The smallest is going to be the most minor axis, and the one that's in between is going to be a semi-minor axis. I don't know. They don't really name them. They did for plane figures, but not there. So that's how I think of it. Longest, shortest, and median. Okay. Now, in this case, the odd man out, the one with the odd sign, plus, plus, minus, that's going to be your axis. Everything's going to go around that. So this would be a hyperboloid of one sheet, and that would be, I got to sneeze, I'm sorry. Yeah. Sorry. Okay. That's your bow tie looking thing, you know, except it doesn't quite come in. But that would be the axis of it. You know, it'd be this kind of thing. Okay.
So in this one, you axis that X.
Okay, this would then be the thing, but now this is two sheets, so they would be completely separate. So if this is the x-axis, they'd be like that. So you could have rearranged and put the odd man out. That was going to be your axis here and here. The longest one here, that's going to be the major axis. Okay. Now this is how I do it. Okay. They usually don't do it this way. All right. Now our next one, in fact, the next two aren't going to have your ones here. And the way they rewrite some of the others are minus one, especially this one. They're going to have zeros. Okay? So this one will be x over a squared minus y over b squared, plus minus z over c squared is equal to 0. Okay? Now that's not how they usually write it, but just to keep the pattern, that's what it's going to be. Now guess where the axis is going to be? Z, of course. Okay? But what is it when it's equal to a 0? Okay? That means, now, let's go back and notice this. Here, the origin can't possibly be on it. Because if that were 0, that were 0, and that was 0, this side would be 0, that side would be 1. Origin can't be there. Same here. Now, for some reason, and I can't think right now why. Oh yeah, right, same thing. 0, 0, 0, that can't be 1 either. Okay. So the origin can't be on this one. Nor can it on this one. Okay? So in none of these first four can the origin ever be part of the figure in these forms. This one, though, it's got to be. Okay. So this was a sphere, ellipsoid, a hyperboloid of one sheet, a hyperboloid of two sheets. This one has to go through the origin. Okay? Now let's think of this. Let's move this to the other side. That's how the book writes it too. Okay? This is just to get it in the standard way we've been doing them all. Let's move to this side, and then what do we have here? When z is 0, of course x and y has to be 0. But when z is anything other than 0, above or below, you have ellipses here and here. And if z is getting, move this over there, getting larger, the ellipses are getting larger. Okay. Now, yeah.
Are the ellipses, do they have to be circles, or
do they have to be circular? Is that what you said? No, that's exactly what I was thinking too. If these two were the same, then these would be circular. They would be circles, not ellipses. But they don't have to be. They can be ellipses. Okay? But whatever you got, it's the same thing you're thinking. It is a cone. Now, it's not like cone like your conic sections. Those would have to be the same. But this is just any old cone, where they have ellipses coming down, coming to a point of the origin, and then opening up going down, because you see, z could be either positive or negative, because you're squaring it, and it's going to be positive. So this is your elliptic cone. It's exactly this, except they move this to the other side. But to keep sort of our standard type form here, this is what it would be. Okay? Now, and what I was sort of, if you write this the other way, and the way the book does, and put the z squared over here with the 1, right, on the purple load of one sheet, move that over there, x squared, yeah, this is equal to 1 plus z squared over c, or z squared over c plus 1, and then you did the same thing here, only you kept these two here, and then moved this up, then you would have the x is 1 minus 1, okay? So one sheet would be this thing plus 1. Two sheets would be this thing minus 1. Well, with 0 in between, that's the exactly in between a 1 sheet and a 2 sheet where it comes to a point there. So that's where it's equal to 0, not plus or minus 1. So that's the other way to think of it. If you go back to, and then I'll put these back on the same axis. This is equivalent to x over a squared plus y over b squared is equal to z over c squared plus 1. This one, I'm going to swap the axes back again and put it the same way. X over a squared plus y over b squared is equal to z over c squared minus 1. If having the z-axis rather than the x-axis like I do here. And then this would be x over a squared plus y over b squared is equal to z over c squared plus 0. It's exactly in between those two. One sheet, two sheets, 1 point. So that would be your elliptic cone. That's why they call it elliptic cone, because these are ellipses above and below. And a circle would be a special case of ellipsis where the two axes are the same. So that's your elliptic cone. Now, how that looks is this, okay? And this would again be with z as the axis, the odd man out is the axis. Now, I can't tell looking at this whether these are really ellipses or if they're circles. Hard to say. A circle is a special case of an ellipse. But what you do see is that when you have your horizontal traces are going to be ellipses. This is a constant, not 0. 0 is going to be a point. But any other constants, z, any other constant, positive or negative, these are going to be ellipses. But if you have your vertical traces, like where y is a constant, okay, these are going to be hyperbole that way, and if x is a constant, those will go hyperbole this way. So it almost gets back to your conic sections, only those have to be circular cones. This is elliptic cone. All right. I don't think they have any problems with that, examples of that, except just the picture. Now the last one. Okay. Now, let's go back to here. Okay. Our last one is last two actually, x over a squared plus y over b squared. And I'm going to write it this way just to keep it in line, but then I'll do it the other way here, is equal to z. Oh, wait, I'm sorry. I was going to do minus z is equal to 0. To get it back like the one before it. Okay? Now, notice what... Now, that's not the way it's usually written. Now, I wish I had written these further up, so I'll go do this at the top. This is how they usually write it. Z is equal to x over a squared plus y over b squared. Okay. Okay. Just like they did for the elliptic cone. Put the z by itself. Now, again, z is going to be your axis. It's the odd man out. But what do you have for, okay, if z was a constant, what do you have? In other words, these are your horizontal traces. Ellipses, right. But z can't be negative, can it? 0 is on this, because you had a 0 here and here, yeah. So 0 is included, okay? But what you can't have are any negative z's, because those are always squared, right? So z is always positive. So this starts at the origin, goes up. Now, what kind of shape do you have? Your horizontal traces where z is a constant, those are ellipses. But where, say, y is a constant, what do you have? Z is equal to something times a squared, x squared. That's a parabola. Okay? Or when x is a constant, you have a parabola. So now you have a elliptic paraboloid, because you have ellipses going up and parabolas in the other dimensions. Okay? That's an elliptic paraboloid. Okay? And there is elliptic paraboloid that way. Let's see what it looks like. This one. Okay? This is elliptic paraboloid. Your horizontal traces, or whatever your odd man out main axis is, going constant on that, you have ellipses. Okay? And then everywhere else, you have parabola. Notice it's not hyperbole because it's not going down. These are parabolas. Okay. Now, go back to the last form, and that would be x over, I can't get it down there, sorry. Okay. I'll do it up here. X over a squared plus y, minus y over b squared. Okay. Minus z is equal to 0. What we have here, and that's not the way we usually write it. We do it just like above, which would be z is equal to x over a squared minus y over b squared. Okay? Now, z, of course, is your... This is a little stranger, you know. All right. Leave that. I forgot to mark you here. You're here, by the way. I just want to let you know. Okay. The bottom half of the alphabet is here. The top half is missing. Now, they'll get an email from Faith saying that she either was or has been very sick. So that may be the reason she's not here. I can't remember if Silva, she may have told me that they were going to be leaving town or something like that and had to leave early. I don't remember what that is. Whereas here, when z was a constant, you had ellipses Here, when z is a constant, what do you have? Hyperbole. Okay, so that's why it's called a hyperbolic paraboloid. Elliptic paraboloid, hyperbolic paraboloid. Okay? And we'll go back and see. By the way, we're right near the bottom of page 673, no, 673, section 12.6, survey of quadric surfaces. Here's your paraboloids. The hyperbolic paraboloid is z is equal to x over a squared minus y over b squared. With constant z's, you have hyperboloids, hyperbole, okay? And not just that, well, here's what we were just saying. Your horizontal traces, let's assuming that z is your axis, are ellipses for the elliptic paraboloid, hyperboloid for the hyperbolic paraboloid. The vertical traces here are upward parabolas on both of them. On this one, upward parabola on one, downward on the other. Now here's why. Let's go back to our formula. When y is a constant, then this is basically a upward parabola, right? Parabola, okay? But when that is, now that's looking downward because the leading coefficient is negative. So that's why you have downward parabola is one, upward on the other. Okay? Whereas in the elliptic parabola, paraboloid, upward, upward. You see? Upward, upward. Both of those are constant. Okay. So that's why this little table works. The upward parabola would be on the positive and the downward parabola on the negative. Okay? And here's what they look like. Again, we already showed this one. I think this time I'm through flicking back and forth, so I'll go and zoom in on it. So it'll be maybe just a tad easier to see. All right. Your elliptic paraboloid, where you have the plus sign here, z to the first power here, only up and upward. Yeah, because z can't ever be negative, or these two are both 0 or positive. Then, and this one happens to have a axis this way of 2 and 1 that way of 3. Not really an axis. Basically, it comes about with your curvature type thing. Okay. Your horizontal traces are ellipses, with the major axis being the y here and the minor axis the x of the various ellipses that are your horizontal traces. But your vertical traces, the purple ones here when y is constant, and the green ones over here when x is constant. Okay, and those just give you parabolas going up and down. On this one, going up in both cases. In this case, z can be negative, can it? When the y over 3 is greater than x over 2. So yes, it can be. So now we have going down that way. Now, this is the weird, yeah, it's totally weird. But here you always could tell where your axis was. What in the world is the axis of that? Okay? You have a certain symmetry around the z-axis, but you sort of also have a symmetry around the y-axis and kind of a symmetry around the x-axis as well. So yeah, this is weird, but z is the constant here, and this is what you've got going. So, they're paraboloids because your vertical traces in both dimensions, when y is constant, your purple traces here are parabolas, but they are going when y is constant, then you have this form. They're going up, but when x is constant, then your paraboles are going down, the green ones, okay? But your vertical trace, your horizontal traces, when z is constant, that's your hyperbole, the hyperbole, and showing that is here, the blue ones. Yeah. You see, you got blue ones above the axis, the blue ones are along x, below the axis, below the xy plane, the blue ones are like this. So you see you got hyperbole like this below the y-axis, and above the xy plane, and above the xy plane, the blue curves are up here. So the hyperbole are along the x-axis. So there's sort of a symmetry axis in all three things. Your axis for your both of your parabolas, the upward parabolas and the downward parabolas, would be the z-axis. The axis for your blue, for your negative z's would be the y-axis, and the blues for the axis for your positive z hyperbole would be your x-axis. So that's why you have a certain type of symmetry in all three dimensions. Now, I don't know if you see it this way when you look at it, but that looks a lot like a saddle. A saddle, right? The horse goes under here and the legs go there. Okay, right? For those who ride, I don't. Okay? Yeah. But this is very similar. I don't know. Maybe we're going to get there. Yeah. If we get, I think we will, get to our partial derivatives, we'll have in three space and stuff like this, when we have those, you can have minima, you can have maxima, and you can have saddle points. This is a saddle point. It's a maximum in this dimension, minimum in that dimension. So that's what we call a saddle point. Well, and here she is. All right, 3/4 of the class here. I think this is my best attendance class. Well, no, the first class finally caught up to 3. Okay. So, Faith had emailed me that she was sick. I don't know if she still is or not, but I wouldn't be surprised. Okay. We just have finished page 673. 2 types of paraboloids. So you'll have to listen to it on YouTube when it gets out there. All right. This, I think, is example 4. I believe it is. Okay? Alternative form of a hyperbolic paraboloid. Okay. And here they've done something that I said we weren't going to do. Okay? But they are doing it in this one. Okay? I'll blow this up so you can see it a little bit better, but then I'll probably be coming back to it. I don't know if I'll write on it or not. We'll see. Okay? Believe it or not, this thing right here is a hyperbolic parabola. I'm sure it doesn't look like it. Until you think back, wait a minute. One of the earliest parabolae that we probably dealt with is y is equal to 1 over x. If you graph on the plane, y is equal to 1 over x, and the xy plane, the first quadrant would be like this, and the third quadrant like this. It's a parabola. You didn't think about it, but indeed that's what it was. First quadrant, third quadrant, everything was symmetric about a line like this, okay? But that was indeed symmetric. Well, so what? Y is equal to 1 over x. But what if you multiply both sides of the equation by x? You'd have xy is equal to 1. So sure enough, xy is equal to some constant. That was hyperbole. It is here too, except that you're not along the x and y axis anymore. You're in the first and the third quadrants of the xy plane. Okay, that's where your hyperbole are. You know, when z is positive, some of them are up here, and when z is negative, they're down there. So how you change this, and I said we weren't going to do any with cross terms. This is the one that we do. If we wrote that as z is equal to u squared minus v squared, how do you get that? Well, from out of the blue, or some unmentionable body part, they pulled this. U plus v is equal to z, and u minus v, no, I'm sorry, is equal to 2x. Sorry, I was looking at the wrong thing. That's not what I want. Okay. All right. 2x, and u, yeah, I gotta say u and write y, because I was thinking y, that's where I'm heading. Okay. U minus v is equal to 2y. Okay. Now, where would you have come up with that? Okay. Well, let's see what happens if you do that. Okay. Our original, let's start this way. Z is equal to 4 times, now what is x? U plus v over 2 times y is u minus v over 2. Okay? So, the 4 and the 2 2's cancel out, right? And what you're left with is u squared minus v squared. So sure enough, that gives you exactly the same form. With this substitution, that gives you exactly the same form. And that, we recognize, is a hyperbolic parabola. Minus sign here, z to the first power there. This makes it a paraboloid. This makes it hyperbolic. Okay? Does that sort of make sense? Now, we haven't done that much shifting of axes before, but sure enough, that gives it to you. And notice this new u axis is exactly down the diagonal in the xy plane. And the v axis is in the anti-diagonal in the xy plane. And sure enough, that is that 45-degree shift that picks up, just like y times x is equal to 1, that if you did a 45-degree shift there, your hyperbole would be along the axis. So that's done the same thing here. All right. Now, let's go to example 5. I think that's probably going to be, no, it isn't. I think the slide set doesn't show example 5, so we're going to have to do that probably on our own. So forget this figure here, okay? That was the same figure 9. And that's figure 11 in our book, so figure 10 is missing. Without referring back to the formulas, use traces to determine and graph the quadratic surface given by x squared plus 2z squared minus y squared is equal to 0. Now, it says without referring back to the formulas, sort of hard to do, okay, use traces to determine and graph the quadratic surface given by that equation. Now, it says don't go back to the formulas. I'm really not. But I'm going to add the y squared to both sides. That does get me back to that, but the reason I do, that helps me see the traces. X squared plus 2z squared is equal to y squared. Okay? Now, here's how it helps me. When I put y is equal to a constant now, not 0, a constant. 0, 0, 0 is on this. 0, 0, 0 is on that. That sort of gives away what shape it is, what quadratic surface it is. It's the only one that went through the origin. The cone, okay? The elliptic cone. So we know this is elliptic cone. What do you think the axis is? The y, the odd man out, okay? So when I write it this way and set that equal to a constant, what does this form? Ellipses, okay? So your vertical trace, when y is equal to a constant, are ellipses, okay? Vertical traces are ellipses. Now, probably easier to go back to this form, and what are your horizontal traces? That's where z is equal to a constant. So if z is a constant, it goes over here. Whatever, and by the way, if z is a constant, it's a positive constant. So you get a mess there. But anyway, what do you get? What's your trace then? Those are hyperboles that way. Okay? And when x is a constant, you get hyperboles that way too. Okay? So your let's use this axis as if this is the one we're doing. The one along the y-axis, that's a constant. I like this one for that. That gives me ellipses. Getting bigger. Through the origin at the point, and then bigger and bigger ellipses as you go out. Okay? So your vertical trace along the y-axis are ellipses. Your vertical traces along the x-axis are hyperbole, okay, because you've got the cone up here and the cone down there. And along the z-axis, which is your horizontal traces, you got your ellipses like that too. Okay? So, indeed, that's what you get. And this, you'll have to look in the book to see what it looks like. All of you got books? Yeah. Oh, except your book doesn't have this figure. You don't have example 5 and you don't have figure 10. But it's, I'll tell you what it looks like. It looks like this, only flip that and put the axis along the y-axis. Okay? And then your ellipses, your cones coming out here, going back there. And you have along the y-axis, you have your ellipses here and there. And then along the x-axis, you have your hyperbole there, and along the z-axis, you have. Okay.
What is the 2?
I'm sorry.
What does the 2 mean?
Okay, the 2 here. Whoops, we don't have it. We're there. The 2, okay? That means for your ellipses, you do like this. Remember, what we're doing is y is a constant, whatever constant you choose. Then divide everything on both, well, this is a constant, divide by 2, and you get x over square root of 2 squared plus z over 1 squared is equal to some constant, okay? So basically that's saying x is your major axis and z is the minor axis, with the be a ratio of square root of 2 to 1, basically, always. So this is like 1.414, and that's 1. Yeah. So it's a little bit, the ellipse is like this coming out, you know, getting bigger, bigger, and bigger, but always a little longer on x than it is on 2. That's what the 2 does. That, it said don't go back to the form, but that would get you back to the form. Okay, now the last topic here is the quadratic cylinder. Okay, quadratic cylinder. Sorry. Well, this isn't just a quadratic. A cylinder. Okay. I don't want to call that a quadratic cylinder. This is just a cylinder, and basically in the xy plane, this is some curve. Now, frankly, I look at that, and I may be wrong on it, but that looks like a cosine curve, right? Looking down at the xy plane, you have a maximum here, equilibrium point, minimum, max. You know, it looks like that could be a cosine curve. It may not be. It's just some curve like that. And but in the xy plane, that's what it looks. Now, it looks like it's translated upward because it doesn't look like this goes back to as far back that way as it's stuck out this way. So you have a vertical translation here of that cosine curve, just some constant added to it, if that is indeed a cosine curve. And the z is arbitrary. So it's a three-dimensional structure, but whose equation looks just like the two-dimensional cosine curve. Or whatever curve you have. Whatever function you have, y is some function of x, or x is some function of y, that would be one going along this way. You would have some curve defined by that shape, and then it extends in the z direction infinitely up and down. That's what we mean by a cylinder. Whereas before, I would have sworn a cylinder had to be closed. No, this is an open cylinder. Okay? You usually think of a cylinder as being a tin can, right? But that's a right circular cylinder. This is a right cylinder, but it's not even closed. It just has a curve in the xy plane, and then the z is arbitrary. It can have any value, but it always has those xy values. Okay. Now, this is just a cylinder. It's going to be a while, but I'll show you some quadratic cylinders. They highlight quadratic cylinders, but they don't show it to you right here. Okay. Oh, right here. Okay, got it. I thought these were going to be separate. Okay, I can't zoom completely. I can't get everything on here, but I can get most of it. All right. Oh, yeah, these are all quadratic cylinders. Okay, sorry. Okay, meaning that all the exponents are 2. Really, we only care about those for the variables. That's a constant anyway. Okay, this is a right circular cylinder. Why do we say right? It parallels, the surface parallels the z-axis everywhere. So it's a right circular cylinder because your base is a circle. X squared plus y squared is equal to r squared. Or you could divide everything by r squared. X over r squared plus y over r squared is equal to 1. Right circular cylinder. Okay? An elliptic cylinder, again, your variables are squared. So this is going to be your your ellipse here, the A obviously is greater than B because the major axis on X, minor axis on Y. This is an elliptic cylinder going all the way up or down. Okay? Z is completely arbitrary. By the way, that would be a right elliptical cylinder. They don't say that, but it is because the sides parallel the Z-axis. So it's at right angle to the XY plane. This would be a hyperbolic cylinder. Okay? This one, have they done this right? No. They've drawn this wrong. How can you tell? The minus. See, in this, Y could be 0. According to this, Y could be 0 if X is equal to A. That's not on here. What they have here is Y over B squared minus X over A squared is equal to 1. And this would be your B. And because Y, if you reverse these two terms, or change the sign of the two terms, however you want to look at it, Y, when Y is equal to B, X would be 0. Because this would be 1. Okay? So that would be Y is equal to B and Y is equal to minus B. Okay? And X is 0 there, either right or left. The way they've drawn this, the way they've drawn this, looking at this, X can never be 0. Not the way they draw it. If X can't be 0 the way this is written, because if X is equal to 0, you have a minus sign equal to a plus sign. That can't happen, okay? So X, according to this, did I say that right? Yeah, X can't be 0. So you couldn't have anything on the y-axis. Here you do. So they've drawn this and wrong. Take these two and just change them to here, and you got it. Sorry about that. Okay? And here's your last quadratic cylinder, and this is the parabolic cylinder. Here only one variable is squared, the other is to the first power. That means y is always positive. So sure enough, you have it. They got this one right. Okay, the y is positive. See, the y, you needed to flip these two, but that one is correct. The y is positive, always positive. X could be positive or negative.
They're flipped on the new edition.
What's that?
They're flipped on the new edition.
I can't hear you.
They're swapped in the new edition.
Oh, they did.
For the hyperbolic cylinder, in the new edition, it's the Y's.
Oh, they did. Okay. I've got the new edition too, but mine's not the paperback. My new edition, same thing, third edition, it still has it wrong. They corrected it in your printing. I think that's just a separate printing from this one. But glad to point that out. Sorry. One of my students in my last class says I'm probably having allergy problems because pollen's out now. But I was telling them, I think it was maybe something else because of something that happened last night. But anyway, okay, I think we've done that. Now, I don't think these are the last slides, okay? No, here we got some more. These are quadrant surfaces. Okay, what would you say that first one was? That's an ellipsoid. What would you guess would be the major axis here? The major one? Looks like to me Z's a little larger. It's hard to say. I would guess C would be the largest on here. And then Y would be greater than X. I agree with you there. But it looks like to me it's elongated along Z. Okay? You didn't see that, did you? What's that? So what? A hyperboloid of one sheet, two sheets. Paraboloid, elliptic paraboloid, hyperbolic paraboloid, and the cone. Okay. Elliptic cone, as opposed to circular cone. Okay. Circular cone A and B would be the same. Elliptic cone A and B would be different. Doesn't matter what C is. Just A constant. All right. Any questions on those?
So what
Oh,
can
yeah.
this be used for?
What's that?
What can these shapes be used for?
Okay. Sort of a good question. I've got to come up with a good answer now. Like I said before, when we're doing partial derivatives, you'll have more than one independent variable with one dependent variable. Okay? And you can conceivably get shapes like this. Okay? And so when you come up with equations that have these kinds of characteristics, that then you can find, here you would find a max and a min in each variable. Here you can have mins in the x's and y's, maximum in the, and min in the z's, minimum in the z's, and in some cases of the x and the y's too. We'll talk about that later. Here you have a maximum when x's are constants and minimums and y's are constants. So, and when you see these things happening, you'll know what kind of shape they are. Okay? So it's a pretty big stretch, but you'll use some of the same terminology. The only one I think specifically is their saddle point. That will be describing that. And they didn't even call it that here, but that's what it is. Okay? And these then are three of your cylinders. I guess the major ones that you would need. The elliptic cylinder, the hyperbolic cylinder, and the parabolic cylinder. You could have a circular cylinder, but it's a special case of elliptic. Okay. Now notice the equations here, they look like two-dimensional equations. But if you're in three dimensions and have that, that means Z is arbitrary. That's why it goes infinitely up and down without regard. It's always going to be that shape in that form. Okay. Homework exercises here. And these are sort of fun, so don't, oh wait, do you want to do preliminary questions? What you think? Huh? Yeah, okay, let's do them. Marcus back there said, nah. Okay, all right. True or false? All traces of an ellipsoid are ellipses. True or false? True, absolutely. True or false, number two? All traces of a hyperboloid are hyperboles. Hyperbolas. That's false because your hyperboloid one dimension, your major axis, the traces along the major axis are going to be ellipses. Okay? Number three, which quadric surfaces have both hyperbolas and parabolas as traces? Oh, that's a tough one. Hyperbolic paraboloid, you got it. Okay, because there's no such thing as a parabolic hyperboloid, so don't go that way. Okay, number four. Is there any quadric surface whose traces are all parabolas? No. Okay? This has ellipses and hyperbolas. It doesn't have any parabolas. So it has to be one of these two paraboloids. This has hyperbolas and paraboloids. This has ellipses and paraboloids. Yeah, you got it. And then the others don't even have any parabolas in them. So yeah, can't be. So that's no. Okay? Oh, I should be checking the answers back here. 12.6. True, false, hyperbolic, paraboloid, what a guess, and then no. Okay, number 5. A surface is called bounded if there exists an m greater than 0 such that every point on the surface lies at a distance at most m from the origin. Which of the quadric surfaces are bounded? Which of the quadric surfaces are bounded? Okay. Here's the giveaway. Go to the origin. Is there some dimension that no matter where you go from the origin, you can always contain that? Yes. Just go somewhere outside your largest value down here. How about here? No, 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 no. These all extend infinitely. So the only one that's bounded is your ellipsoid. Okay. Make sure they got it right. Yes, your ellipsoid. Number 6. What is the definition of a parabolic cylinder? What is the definition of a parabolic cylinder? Yeah, there's a formal definition, but just give me a quick and dirty on it. In one of your coordinate planes, usually x, y, but it doesn't have to be, is defined by parabola. And then in the other dimension that's not in that plane, it goes infinitely large and small. Okay? Here is a parabola in the xy plane, y is equal to ax squared. Okay? That's along with y as being the axis of symmetry. Okay? And then z goes infinitely in both directions. Okay? I don't know if that's what they wanted, but that's practically what it is. All vertical lines passing through the parabola C in the xy plane. Okay. Yeah. I don't like them saying vertical lines. I'd say all the lines parallel to the z-axis pass through the parabola C in the xy plane. That, because, I mean, you can orient xyz as long as you have it right-hand rule. You can orient any way you want to. All right, homework exercises then. Do any of the odds 1 through 5. They are fun. Do them. Any of the odds 7 through 11, they are pretty much fun. Do them. Any of the odds 13 to 19, and again, pretty much fun. Then any of the odds, well, either 21 or 23. You choose, or both. Either 25 or, no, any of the odds 25 to 37, you choose. And then any of the odds 39 to 45. Okay? Now, if any of you ever, in your engineering or whatever major you're going into, you need to deal with cylindrical and spherical coordinates, next section deals with that. They're pretty straightforward and not that difficult to use, but it would take a little bit of time to go over all those. So go through that, read through it. I'll let you, but you're not going to be tested on it in this class. I'll put it that way. Okay. So let's move on. Oh. Emmanuel was supposed to remind me that when y'all came in to give you the test, and he was going to try to take the test all by himself and leave y'all out. So you need to watch this guy, okay? Here is your second test. Okay? Okay. And by the way, if you need it, 1 and 2 are from 12:1, 3 and 4 are from 12:2, 5 and 6 are from 12:3, 7 and 8 are from 12:4, and number 9 is from 12:5. I think that's pretty close. Maybe off a little bit, but I believe that's correct. Okay? Now, your next test will have 12:6 on it, plus what we do in 13. So let's get going to 13. Okay. If I can respond. There it goes. Okay. One more. There we go. Chapter 13. Chapter 13. Chapter 13:1. Section 13:1. If it'll open. All right, we are now open. And almost sort of ready to go. All right. Calculus of vector-valued functions. Hopefully this will be a pretty seamless continuation from Chapter 12. Okay? That's what we're dealing with. Now, both in your book, somewhatly, and here, again, somewhatly, these are dealing with basically they're using as the example here DNA. DNA polymers form helical curves whose spatial orientation influences their biochemical properties. Y'all are probably a lot more versed in DNA than I am, because it was a fairly new thing back when I was taking biology in high school. I never took any biology in college. So we just barely got a little glimpse. We didn't know anything about helical curves and things like this, but I think you'll know that you have certain symbols, and one's on one string and one's on the other. I don't know if they call it inner and outer. I don't see how they could, because they twist around. But there's certain things that can be on one end and certain things on the other end, and what those various combinations are then give you the things like hair color and body shape and and all these other things, your tendency to do this or that the other way, for instance, I can't jump, so that gene is just completely broken in me. Yeah, so anyway, those kind of things. All right, that's the little lead-in for whatever use that was. All right, what we're going to look at is vector-valued functions. Okay, and here's an example of one. Consider a particle moving in R3, that's in space, okay, whose coordinates at any time t are x of t, y of t, and z of t. Okay? It's convenient to represent the particle's path as a vector-valued function. Now, right there, whether you realize it or not, you probably don't, you have something that is going to be a little ambiguous. Okay? Notice they said represent the path as a vector-valued function. Okay? Now the way they've written it here, that R of t, they've written it as if that's a vector, because that's bolded, right? And they put the vector components on here. And x of t is the horizontal function of that. Y of t is the second horizontal function. Z of t is the vertical. You could have also written this as x of t I plus y of t j plus z of t k, where I, j, and k are the unit vectors in those three dimensions. Standard. Either of these are fine. I actually prefer this a little bit because I don't have to bold or put carets. You see, I can't write bold, so I put a little hat on top of the unit vector. Okay? R would just have an arrow over it, because I can't write bold there either. In this notation, I don't have to do any of that. I just write down the components. But they're functions. Okay? So here would be a representation of that, such a path of such a vector valued function. Now here, they're not making any special big deal about it, but it really is a little bit of one. When you call it a vector valued function, realize this. It's a function of t, not of x, y, and z. Okay? Now, t doesn't have a dimension here, does it? So the concept of not backing up on itself really has no meaning here. This curve certainly can back up on itself many times over. It can even connect somewhere here and start repeating itself, and it's still called a vector valued function. Even though for any value of x, y, or z, you could have that doesn't specifically define an r, okay, a specific r. But for any value of t, it defines a particular place on that curve. Okay, so t is your independent variable. R kind of is your dependent variable, and x, y, and z are kind of like intermediate type variables. Not independent, but not dependent. They're dependent on t, but they're independent variables of r. I mean, so they're kind of in between. So basically, all you're graphing is your r in space as a function of t, which doesn't have a dimension here. So there's r of t is r of t1, r of t2, r of t3, to the r of t4, something like that. Some other r of t, a generic r of t. R of t0 could be back here. R of t to the minus 1 could be over here. I mean, this is just a marker saying which t you're talking about. Okay? The function can be decreasing with r could be decreasing with increasing t. It could be increasing with increasing t. Yeah. So lots of things could be going on. Okay? Now, the r's are these blue vectors here. The path is the pink curve. Okay? And you can use the terminal points of the r to define the path. You see, the path really isn't a vector, kind of. It's defined by a vector. Okay? That's where you get a little bit of a problem. All right, so let's introduce a few other words here. The variable t is called a parameter. It's the independent variable in the thing, but it's also called a parameter, because x depends on it, y depends on it, z depends on it, and of course r depends on it. But r depends on x, y, and z as well. You have to figure out what t you've got, what parameter t you're dealing with, and then enter this function that tells you where you are on the x-axis, enter the same t on this one that tells you where you are on the y-axis, enter the same value on and the z function that tells you where you are there, and those 3 points define where you are on the curve. Okay? So, it doesn't have an axis, but it's your independent variable. It's a little stranger. Okay? The x of t, y of t, and z of t are now the components or coordinate functions. Okay? Component functions makes more sense when you're thinking in terms of variables. Coordinate functions makes more sense when you're thinking in terms of the path. Okay? So the vector function, they would be component functions. If you're thinking of just the path or a point in space, they would be your coordinate functions. So they could be either or both of those. Okay? Now, that variable doesn't have to be t, by the way. Okay. Here they give a couple. Let me see. Nah, that'll be this one. Whoops, let me get my pen back. Okay. You could have r of t is equal to, it is a vector. These are the terminal points on a vector. T squared e sub t, e to the t 4 minus 7t. So for any value t, you can come up with a set of components for the vector r of t, or the set of coordinates for the point on the curve, the pink curve there. Okay? Again, it doesn't have to be t. You can use other letters as well. They love using r for the vector. That's pretty common. It could be r of s. S now could be your parameter. And this could be something, they just chose different functions, square root of s, e to the s, they like that one obviously, and s to the minus 1. All right, now, time out just a moment. On the first one up there, t's could be all real numbers. They don't have to be. You could limit them to a certain range, a certain domain of t, but they could be any real number. There's no restriction on the t. How about your s's there? Okay, they have to be positive. This would just have to be non-negative. It could be 0. This could be anything, but this can't be 0. So this can't be 0, this can't be negative, so that makes s have to be strictly positive. So it can't be 0, but it could be anything greater than 0. So say if you had to pick limits, say from 1 to 5 or 1 to 400, or anything such as that, you just couldn't include 0 or any negative number. Okay. So your domain on this one is the set of all real numbers. Okay, that's the domain of t. The domain here of s is how do they say it? The set of all s's. I can't write. S's in the real number system, as long as such that s is greater than 0. Very good. Okay, can't even be equal to 0. Okay, now one other little comment before we turn the page. The terminal point of a vector valued function r of t, for instance in that figure there, traces a path in R3 as t varies. We refer to r of t either as the path or the vector parameterization of a path. So again, a little bit of weaseling on the words. We sometimes refer to it as a path or sometimes the vector parameterization of a path. We shall assume throughout this chapter that such points of r of t have continuous derivatives, okay, within your domain. Obviously, this doesn't have a continuous derivative if you count s equals 0 or s negative. But that's not in the original domain. Within the original domain, yeah, that has continuous derivatives. Okay, as long as s is greater than 0. Not equal to and doesn't include any negatives. Okay. Some special cases of vector parameterizations we did in chapter 12. For instance, you tell me what this would represent. Going back to our t, that's their favorite. Okay? What would that represent? I'll write it a slightly different way too. I don't know why they use A, but it's fine. I wouldn't write it that way, but that's how they do it. I'm trying to keep it the same way as the book. If I were doing that, instead of A, I would have said V sub X. The V component of the X component of the V vector, okay? Y0 plus V sub Y, T V sub Y, and otherwise I would have written the A in front, because that's a constant. And T is a variable, so I would have written AT, X0 plus AT, Y0 plus VT. But I tried to do it really quickly. Okay, what does that represent? A straight line, okay? Going through the point, X0, Y0, Z0, and in the same direction as the vector V. Okay, yeah, we did that before in chapter 12. Remember? Okay. Back in chapter 11, I think we hit on this. We talked about parameterized curves. C of t is equal to x of t, y of t, where those were coordinates of a point. Okay. Now we just got a moving vector r of t that changes, whereas c of t was a fixed curve. Now r of t, the point of which traces a fixed curve. Okay. Now, it is important, this is the paragraph right above example 1. It is important to distinguish between the path parameterized by r of t and the underlying curve c of t traced by r of t. Boy, is there a difference. The curve c is a set of all points x of t, y of t, z of t, those are points in parentheses, as t ranges over the domain of r of t. The path is a particular way of traversing a curve. It may be traversed, the curve several times, reverse direction, move back and forth, and so on. So the r of t has a little bit different meaning from the curve c. Curve c is just a collection of points. The r of t could be going clockwise, counterclockwise, up, down. It could be doing a bunch of different things. So I think this may be example 1. Let's see if it is. Describe the path of r of t is equal to cosine t sine t 1. Yeah, that's it. Where t is any real number in the world, from negative infinity to positive infinity. Okay? Now, I hope to answer sort of Emmanuel's question that you could look at this and say, oh, that's a right circular cylinder, center of 0, 0 at the origin of the z-axis is probably the better way to say it. But you're taking the horizontal trace where z is equal to 1. So in that sense, you can think of this as one of the quadratic surfaces, a cylinder, right circular cylinder, but you're just doing the trace of z is equal to 1. Okay? And basically that just describes it. Okay? Notice this is your x coordinate. It starts at 1, and then it goes down to 0, to minus 1, to 0, and back to 1 again. One time around t0 to pi, 2 pi. Sine, on the other hand, the y value starts at 0. This is 0 on y, increases up to 1, decreases down to 0, goes to minus 1, and back to 0 again here. So that's one cycle or period of sine as t goes from 0 to 2 pi. whereas the z is 1 and only 1 stays 1, so you're up there at that vertical trace, horizontal trace, where z is equal to 1. Okay? Now, the path is looking down from above, rotating counterclockwise. So that's where the vector parameterization also has a direction. The curve is just that circle with no direction associated with it. It's just a collection of all these points. Again, not a big deal, but they sometimes make a bigger deal of it. Okay, they did all the work there. And t is going from negative infinity to infinity. Okay, it's just going round, forever. Okay, it started back at negative infinity and still doing it. And hasn't got up to halfway to never mind. Okay, so the next question: how are the path and the curve traced by r of t different? I think I just gave it away. The path has a direction. The curve is just a collection of points. Okay. Let's see if that satisfies. The underlying curve trace with that is the circle itself, and the path is if t is it's going round and round and around the circle over and over and over again, but it still traces that one circle. Okay. Now, this is getting to the realm of things that I'm glad they're drawing these, because I sure would give up on it before I had these drawn very well, if I could draw them very well, which is somewhat doubtful. Okay, that's about as good as I can do here. All right. Here is, believe it or not, a curve. This is one curve. 3 views of that curve. The curve r of t is this one here, t sine 2t cosine t, comma, t sine squared t, comma, t cosine t. And this is going from 0 to 4 pi are the values for t. This is the same curve, but looked at from 3 different viewpoints. I'm so glad they're drawing these. It would drive me nuts to have to draw these. Now notice they all have right-hand rule orientation, x, y, z, x, y, z, x, y, z. Yeah. Positive x is back there now. Okay. This is sort of what they call isometric. This has another name I don't remember, but the xz plane is the board and x is coming. I mean, the yz plane is the board and x is coming out and going back into the board. And here, x is going in, positive x is going into the board, and the board is the yz plane. So the positive y is this way. Okay. So even that is difficult to do, because you would think this would be, if you rotated this 180 degrees this way, you should get that, but it shows the x. You see, you can't show the x going into the board, it would just be a point. So here they've shown the x on this side, and there they've shown the x on this side too, so that wouldn't be the case if you did that. Even that is really hard to talk about. Okay? So, what I do, and this is what I suggest you, start with t equals 0. I can't remember if they gave us, yeah, here it is, 0 to 4 pi. So when t is equal to 0, your x is 0, right there. Your y is 0, right there, wait, yeah, 0, right there. And your z is 0, right there. So you're starting on the origin in all 3 circumstances. Now your t is increasing a little bit. Let's have an increase to pi halves. It's a good one to do. So sine of 2 times pi halves is what? Pi, sine of pi is 0. So your x is 0 again. Boo hiss, okay? Your y, though, is pi halves times sine of pi halves is 1. 1 squared is 1. So this is going to be pi halves. So your y, when x is 0, your y is pi halves. What it's done, it's gone back here and come back here again. Now, it looks like x went negative there. That doesn't sort of feel right here because from 0 to pi halves, the sign, this is going 0 to pi halves, which is positive. This is going 0 to 0, but staying always positive. And this is going 1 to 0, which is always positive. So something looks pretty wrong in this, okay? But it's okay. This shows it better. That's why this is not a good view here, okay? In fact, that just totally looks wrong here. It looks like it could be better here, but it's hard to see. This one you see it pretty well. Positive x coming back and going to 0 there, okay? X equals 0 there, okay? So that's that first loop from 0 to pi halves. Let's make sure that works here. This would be pi halves. That would be where you are on y. And this would be pi halves times 0, so you're 0 on z. And sure enough, you're not up or down there. You're not up or down there. You're not, it's hard to say here, but you all wiggle in there. Okay. And then you go to pi. And you just keep going up, I would say about half pi's, and trying to find points here. And here's what you'll notice. On your x, none of these show x very well. Okay? So it's sort of hard to see what's going on x. On the y, you have an intersection with x0 and z0. You have a 0 on y here, 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 and here. Okay? So definitely x equals 0 and z equals 0 there. At a very regular spacing, your y would be, so you'll see these kinds of things. Since this was your initial thing and it's doing all this kind of weird stuff, this must be t is equal to 4 pi. And you could go back and check that, and I think you'll find that to be the case. 4 pi cosine is 1. This would be 4 pi, so you're 4 pi on z, and you should be 0 on the other two, because this would be 0, and that would be 0. So sure enough, that's, so your z, you have, it starts at 0, and then does whatever it's doing here, slightly positive here, but then it goes down, up, down, and up. Okay. So sort of figuring here, 0, probably pi, 2 pi, 3 pi, 4 pi. That probably is going to fit you there. Here, 0, pi half, no, pi, 2 pi, 3 pi, 4 pi. No. These are your half pi. 0, pi halves, 3 halves pi, 5 halves pi, 7 halves pi, before you get to 4 pi. So you can get a general idea of what's going on there. Same thing here, 0, pi halves, 3 halves pi, 5 halves pi, 7 halves. So you can kind of get, this tells me absolutely nothing. I get dizzy looking at that. Okay. But you still see the z does have 0, pi, 2 pi, 3 pi, 4 pi. See, this comes in front. This one comes in front. This is the intersection. This one, this one, this one, this one, that one, that intersect. These others are just passing by, without intersecting. So that's the problem with trying to graph 3 dimensions on a 2-dimensional plane. Okay. Oh, man, I talk too much, don't I? Okay, but that's a space curve, okay? Really hard to illustrate on a 2-dimensional plane. It looks like we're going to have to start next time with example 2, okay? And let's see, did we get enough done to do any homework exercises here? I think you can do 1, 3, 5, 7, 9. I think you can do 9. Maybe I'd stop there. Okay. Yeah. Okay. So you get a little bit to do. I want you to have plenty to do over the week because I know you're going to miss being here terribly. Okay. So take care. Have a good spring break. Be safe. See you in a week and a half or so. All right. Good deal. What's that?
So when is the next day we going to be start?
Let's see.
April 3rd?
That sounds about right. Let me think. 23rd, 24th, 25th, 26th, 27th, 28th, 29th, 30th. See, April has 31. No, it's all like the 3rd or 4th. It's next week is spring break.
Yes.
So the first week in April we're back. Okay. Oh, okay. All right. Do you need it today?
Yeah.
Okay. All right. We'll catch you later. Let me